Yes, welcome. Good morning and good evening. Thank you for joining today's webinar for the Transatlantic AI Hackathon. I'm Jay Burris. I work at Intel as an academic program manager for OpenVINO, which is our AI Inference Toolkit. Stands for Open Visual Inference and Neural Network Optimization. And my partner in crime along the way in this hackathon series is from Luxonis. Eric Kokaj is a depth AI software developer. And we've paired together to bring you really leading edge software and edge equipment that you can use and will use, the selected teams will use in the hackathon. So we'll talk a bit about that. So a bit about Intel. At Intel, we're about world-changing technologies, and we really want to create world-changing technologies that improve the life of every human on the planet. Now, tech has never been more important to humanity. In the 90s, we started about digitizing everything, then we went to networking everything, then the mobile revolution happened, and the cloud everything. The cloud has revolutionized everything. And really, we're moving into this inflection point where we're having 100 billion intelligent connected devices that distribute intelligence and that complement the cloud and that are networked by all the network infrastructure we've established. And mobile is just one part of that intelligent connected devices. That leads to an unprocessed data in terms of untapped potential. The world creates 2.5 quintillion bytes of data every single day, but only a fraction of it is utilized. So Intel's about powering digital disruption in the cloud, in connectivity with 5G and wired line network capability, in AI, and in the intelligent edge. And this hackathon and the scope of today's webinar really kind of focuses on AI, but AI is being driven in those three other pillars, transforming the network to have it be processed faster at the edge. AI is being driven into the cloud, and our OpenVINO toolkit can be used both in the cloud and the edge. And that's really what's driving an intelligent edge. So let's talk a little bit about AI inference with edge or with Intel. So computer vision is one form of AI. There's many other forms, but computer vision is changing industries such as emergency response to be able to respond to real-time emergencies and help crime response, reduce crime, respond to wildfires more effectively, for example, things that are going on in the world right now. Healthcare, we're revolutionizing patient outcomes by being able to detect diseases much more sooner with computer vision, whereas the naked eye can't as quickly. Retail is being transformed, such as experiences in retail with frictionless and touchless capabilities, where the pandemic has driven a need to change in some ways the way we shop, and many other areas as well in many other industries. There's many approaches to analytics and AI, and first I like to stop at what defines AI. Here at Intel, we define AI as both machine learning and deep learning. Deep learning really being a subset of AI. And today's webinar is really about deep learning. It's about neural network processing. And the types of deep learning that we'll talk about are image processing, but with the OpenVINO toolkit, you can also accomplish speech processing and natural language processing. You can accelerate recommendation systems as well. So there's a lot of different types of AI to consider. A little bit of a difference between machine learning and deep learning. So machine learning is a bit more basic, if you will, defined by certain sets and defined by those algorithms. Some of those algorithms being math use cases, random forest, decision trees, and so forth. And in this diagram, we show in machine learning how you might identify a person by the roundness of their face, their nose width, their jawline, and use some of those classifier algorithms that are predefined to come up with the result of Arjun. In deep learning has really been the study of how the human brain operates and processes data by different layers and different nodes that may be interconnected, multi-connected. Neural networks can be forward propagation, backward propagation, all sorts of ways to do neural networks. But it's a much more complex way of using compute power to come up with the same result of Arjun. Now, one way I like to describe how a convolutional neural network architecture is defined is actually documented in a great article that I recommend you go read. It's on Towards Data Science by Sumit Saha, and you can find it by Googling him or Sumit and Towards Data Science. And really, CNN architectures are defined by, in terms of an image classification, you start out with an image, and an image is made up of several layers, like red, green, and blue. And to get to processing, you ultimately have to get to processing how computers process, in ones and zeros, in a very flat format. So how do you take a complex workload and flatten it out to be able to process it quickly? Well, CNNs help us reduce the image into multiple layers, such as convolution, ReLU, pooling, and to repeatedly do that to flatten out those layers, and then ultimately to process that, because we know that compute is still a finite power, even though every day compute power grows. And ultimately, we're trying to identify the same things of high level and low level features such as edges, color, gradient, and orientation. So why deep learning? Well, in image recognition and in speech recognition, the power of computing has really allowed us to apply deep learning to be better than the human can do it. So the green dotted line is sort of the human perception in image and human perception in speech recognition. And our human perception is not really increasing, right? But computer recognition is. And this is leading to 13 trillion in additional economic impact by 2030, as predicted. So there's a lot of different considerations to keep in mind with AI. Multiple workloads, so you have to decide what workload profile fits your needs and fits your compute power. You have to define and identify what requirements you face, such as scalability. You want to define an application maybe that can scale both edge and cloud, can scale from a small footprint to a large footprint. You need to fit into the throughput of your device that you've selected, or that you know in the environment where you're deploying it. Maybe you're deploying your device in a temperature constrained environment, maybe at the very far edge of out in the wilderness, for example. And then maybe that platform has only a certain amount of compute power because it can only be powered for a certain amount of time based on battery power and so forth. So you need to decide how to use your compute power and your demand in a scalable way. And at Intel, we don't believe in a one-size-fits-all. There's lots of different compute architectures that can deliver performance for AI, such as CPUs and GPUs and VPUs, which is a vision processing unit. And the VPUs is the Intel Movidius Myriad X chipset that's inside that Luxonis part that the selected teams will receive. So with AI inference, we don't believe in a one-size-fits-all, but we do believe you should maximize the power of your CPU if you have it. Some devices won't, but many do. For example, if you have an Intel-based laptop, it will have an Intel CPU on it and an Intel integrated GPU. So right there's two architectures to utilize. And when you're learning about OpenVINO through this hackathon series, you can actually utilize and start learning with the OpenVINO toolkit on your own Intel-based laptop. There's another architecture, the VPU, which I mentioned. So you can optimize your workload to take advantage of potentially all three. And you can develop your application. You want to simplify your software, your data pipeline, your analytics AI, and your support. And OpenVINO allows you to do that. It's a toolkit that scales to all those different architectures. But in some ways, it really abstracts it for you to very simplify the workload, so you can just specify the architecture you want to deploy it to based on what architectures you have in the device that you are wanting to deploy to. There are challenges in deep learning. There's unique inference needs, there's integration challenges, there's not a one-size-fits-all. And so there can be gaps in low performance to low power accuracies and deployment, can lead to slow time to solution or slow time to market, or in your case, slow time to project. And it can hinder your ability to sort of meet the use case requirements. But with the OpenVINO distribution, it supplies you with a high performance deep learning inference for all those different architectures. It's a really streamlined development, ease of use case toolkit. And again, once I said, write once, deploy anywhere. It really leverages all the different instruction sets in all of the different architectures under the hood, so you don't have to figure out how to code to all of them. And it leverages all sorts of different frameworks, common frameworks for AI inference in the market. You may be familiar with TensorFlow and PyTorch and many others to do that for you without you having to stitch together your code to be able to deploy it. So with the OpenVINO Toolkit, we're deploying it in lots of different industries. It can be used in industrial use cases to enable safer and smarter use cases, such as machine vision, where autonomous robots, for example, have to navigate a warehouse around humans in a safe manner. Machine vision can be used to detect defects in parts. In health and life sciences, machine vision can be used in X-rays and MRI to really detect maybe disease emerging in those X-rays, whereas a human can only see to a certain level. Machine vision can see at a much more granular level. In retail, we're creating safer retail experiences, particularly related to the pandemic, and in safety and security as well. Things such as improving public safety. One of the big use cases that has cropped up in the last year with the pandemic was really, identifying, say, somebody wearing their PPE, so their masks, but also AI can be used in conjunction with sort of heat-based cameras to identify if somebody may be experiencing a fever. So with OpenVINO, there's sort of three phases. There's build, there's optimize, and deploy. So I'm going to go over some of those three phases for you. So there's in the build phase, there's this idea of bringing in a trained model. So with OpenVINO, you're not training a model. That happens in the stage before that. With AI, there's sort of like at the high level, there's the AI training phase and the AI inference or deployment phase. So with OpenVINO allows you to accelerate train models to run it on the Intel architectures. And the two core components of OpenVINO are here in the purple. So there's the model optimizer, which you use a trained model and you run it through the model optimizer, and it outputs an intermediate representation file of .bin and .xml. And that's important because that allows for the Intel architectures that you can see on the far right to understand that model. It's sort of a translation. And it does so with no to very little accuracy reduction. The second core component of OpenVINO is the inference engine. The inference engine is the suite of APIs, essentially, that you build into an application, that you deploy into an application on a device at the edge, or like I said, OpenVINO can and is being used in the cloud as well, but really to be deployed in compute in the runtime environment, to be running that model over and over again as it's defined to do what it's defined to do. To really use that API suite for this we deploy a multi-device plugin architecture to essentially streamline this, so you don't have to figure out how very differently you might want to deploy to Xeon or a GPU, one of our integrated or our discrete GPUs, or the Movidius VPU. And the last image is actually the GNA, stands for Gaussian Neural Network Architecture. It's what accelerates speech and language. So the model optimizer is a Python-based tool. It really imports a trained model and converts it. And the inference engine is this C, C++, or Python API suite that you deploy in runtime into an application. And we'll talk a bit more in depth about that. We'll also talk about trained models. If you so choose and train your model, you can bring it in. But we also have a ton of pre-trained models to start off with in our open model zoo, over 200, which is a great place to start, particularly for this hackathon. So under the hood, I mentioned build, optimize, deploy. And in the build phase, you bring in a trained model, maybe based on TensorFlow, Caffe, Caldi, MXNet, or Onyx. And Onyx is a unique architecture, which we'll talk about a bit, but it expands the scope of formats that you can use. Plus, we have our open model zoo of more than 200 pre-trained models, public and Intel. In OpenVINO, I already mentioned those two core components, but we also offer a number of additional tools. That's why we call it a toolkit for additional training and optimization. OpenVINO is really comprised of Intel code and also open source code, some libraries from OpenCV and OpenCL, and code samples and demos. And then in the deploy phase, I mentioned we have this multi-architecture plugin capability, and the inference engine maps it to those different plugins for you. You just have to specify the device. So let's talk a bit about build. So I mentioned the supported frameworks. So natively, OpenVINO supports TensorFlow, Caffe, MXNet, Caldi, and Onyx. Onyx stands for the Open Neural Network Exchange. Onyx allows for a number of other formats, such as Caffe2 or MATLAB. PyTorch is a really big one that's very popular right now, and many others. So what you can do is you can adopt, in fact, a pre-trained model from the Onyx library of pre-trained models, or you can convert a PyTorch model to the Onyx framework, and then you can run it in OpenVINO, or you can convert it through the model optimizer to output the intermediate representation as well to run it into OpenVINO. So in the optimize phase, the model optimizer I mentioned really translates a model to this XML and bin, two files that describe the network topology. So the model topology and the weights and biases specific to that particular model. And it does some optimizations like linear optimization fusing, stride optimization, and group convolution fusing, really to try to streamline that model to have it run the fastest on Intel architecture. Sometimes there can be layers that can be eliminated or compressed to really streamline that model.
AI models come in a variety of sizes, kind of called quantization. Well, different architectures require different sizes, so a bit of important information to remember when using the Luxonis Depth AI OAK-D-like device is to use an FP16 or floating point 16 model size. You can see in the chart, CPUs generally support all sizes. GPUs also do, though they prefer FP16. Our VPU architecture, our Vision Processing Unit architecture, requires an FP16 size. And you'll use the model optimizer to do that. A little bit of code down at the bottom sort of explains how you use the model optimizer, the Python command mo.py on the command line. You use the raw model, in this case, in the code, it's saying it's a ResNet 50 Caffe model, specify the data type and where you want the output to go. You'll use that as input into creating your blob for use in the Luxonis Depth AI OAK-D-like device.
So in the deploy phase, I talked about the inference engine. The inference engine is really sort of a runtime capability that you build into a bigger software application. The runtime is a core object that performs the AI inference. And you can spin up actually multiple core objects maybe in your application. It all depends on how you define your application. So it runs the AI model based on the images of your input or video of your input, and video is really just a string of images together, or audio as well, to do things like identifying pedestrians, listen to voice commands, Many devices that we have in our home are doing that. Classify objects. Think about a smart doorbell. That's a device that's implemented AI inference to constantly track people coming to the door. And then, of course, the action of ringing the doorbell may trigger an action of connecting to the homeowner and their smartphone, and connecting a voice and sort of a video conference call, if you will, over that device. AI can also do things like track objects and many more. So you build it into the software application, and the software application is really going to be defined to store and process and forward data, react to requests based on what you want your software application to do, and trigger other actions. The inference engine really takes the input, the video or the images or the audio, and then provides insights back to that software application. It's building smarts into your software application. Now, with the Inference Engine API, there's a common workflow. First, you create an Inference Engine core object with a simple command, IE equals IE core. So you've set up the parameter of IE. You read the intermediate representation, and the API is defined here as the IE.read _ network, and you're reading in the model XML file and the model bin file. You prepare your inputs and outputs into blobs, and then you load the network. So through the API, you load the network, specifying the network that you had already specified of reading in the intermediate representation, as well as specifying the device name. The device name meaning, are you running this to VPU? Are you running this to CPU? Are we running this to GPU? So the architecture that you're running it, and the number of requests as well. Then you prepare your input frames, in this case in computer vision. You prepare your frame. Models are typically defined to accept a certain way of that input to be formatted, meaning a certain size, the height and the width, how many channels. It's also, you may need to format it, and you can use OpenCV, which is an open source computer vision library that is incorporated inside OpenVINO to do things like resize it through the API of computer vision. cv2.resize is that command. You can transpose it and you can reshape it. Then you'll run inference, you'll process the results, and you really make that the inference loop running over and over again on that device. So it's constantly running, looking for the input to trigger whatever that model is defined to look for. Now, with the Luxonis devices, the common workflow is a bit simpler, and it's partly why we chose to collaborate with Luxonis and these smart camera, depth-capable camera devices for this hackathon. So with the Luxonis devices, you use a pre-trained model again. You can use one from our Open Model Zoo. You can certainly bring in your own trained model and model optimize it using the model optimizer in OpenVINO and convert it to FP16 if it needs to be. Then OpenVINO supplies a capability called myriad compile to really compile the inference engine blob through that command. That blob is the input into the Luxonis device. So you set the blob path, and then you deploy it into the Luxonis device, and you observe the inference in action. There's two corresponding instructions that are available out on Luxonis's docs.luxonis.com website. You can read on about how to deploy and run their default models, or there's an article that teaches you how to run an Intel pre-trained or public model as well.
There's an easy-to-use joint workflow between Intel's and Luxonis's technologies. Start with GitHub and the Intel Open Model Zoo with over 200 Intel and public pre-trained models for things such as object detection and recognition, human pose estimation, action recognition, text detection, and more. You can use the Intel DevCloud, and you can download those models directly to there, and you can do your development in the DevCloud. OpenVINO Toolkit is already installed in DevCloud. You can learn from the Jupyter notebooks inside the DevCloud, upload models, datasets and code, develop your inference engine input blob, which is what is required to go into the Depth AI OAK-D Lite, and you can also download to your host device. You download your inference engine blob to your laptop, which is your developer device, and then that's the input into the Depth AI OAK-D Lite target device.
OpenVINO also offers some other additional tools. The model downloader tool, I kind of referred to it. You can download the models easily. So OpenVINO in our DevCloud, you can download models, but if you install OpenVINO on your Intel-based laptop, you can do it there as well. But you can also do things like benchmarking your app to measure performance, throughput and latency. You can check the accuracy of your sort of the original model versus the converted model after you've converted it using the model optimizer. And then there's the deployment manager, which really generates a runtime package for you then to deploy to edge devices. There's other tools included, computer vision annotation tool. You might have a whole data set of images or videos that you might want to annotate before training. There's a deep learning work stream, which is really building a more complex media pipeline. So sort of the media comes in, you have the codecs, you might need to reframe, then you do the inference, and then you might need to send that output to some other device to display. We also have compression frameworks for neural networks, training extensions as well. So a lot of capabilities built into the OpenVINO toolkit. So let's get practical and actionable. For starters, I mentioned over and over again, a great place to start is our pre-trained models, all on GitHub. So we make these all free. Take advantage of the model downloader. We don't pre-install all the models with OpenVINO when you install it because it would bloat the size of the installation because there's just so many. So we offer this downloader tool so you can pick and choose which models you want to download. There's GitHub articles that explain how to do that as well. We also have demos and reference implementations of sort of applications that have inference built into them. So you can look through these applications, you can see how they're coded, examples for C++ and Python. So a lot of different use cases, things like detecting flaws in objects, parking lot counters, people counters, and so forth. Now, we have a lot of different Jupyter notebooks. I don't know if many of you probably all aware of Jupyter notebooks, some of you maybe are new to it. And Jupyter notebooks are this great way to learn because they're sort of narrative written explanation surrounded by executable code. And we have, I think, about 12, and I'm giving you a sample of 8 here to get you started. These are also on GitHub, and you can use these with OpenVINO on your laptop. So for example, we have a starter one to start with Hello World. Then there's one on the OpenVINO APIs. And then there's one on converting a TensorFlow model to a trained model to the intermediate representation, and one as well for PyTorch. We have a Jupyter notebook on training a TensorFlow model, and then using OpenVINO to deploy the inference, and several others, model optimization and the model tools. So now I'd like to switch to sort of go to my screen to talk about the Jupyter notebooks. So I mentioned a great place to start here is if you Google Intel OpenVINO Jupyter notebooks, you'll find this page for OpenVINO toolkits and OpenVINO notebooks. And you'll find them all listed here, similar to what I just showed you on the slide. So the Hello World, the OpenVINO API, and a number of others. To set up your system for these, if you install OpenVINO, you will have installed, for instance, if you can use OpenVINO with Windows or Linux. In the case of Windows, you'll install CMake and Python and Visual Studio C++ in the installation instructions, and you'll be able to deploy these. So if I were to go to one of these, for example, let's go to the OpenVINO notebooks one. So you start here, and there's a little bit that tells you about the flow of this Jupyter notebook, the high-level flow of it. And if you go to the README, you can view essentially how the Jupyter notebooks when you run it live. Just make sure I get to the right. The hello world is maybe a better starter place to get here. So if you go here and to README, you'll see an introduction of this particular one, and it shows you sort of this image that's going to be used, a flat coded retriever, and it's going to do inference on this image. So after you set up your installation, you can go through the installation steps in this Jupyter Notebook. And it shows you what's inside. It shows you how to get started. Apologies, I'm on the wrong page. And you can follow the installation instructions to get going. So I have already started and done an installation of this hello world. And if I start it, it should open a Jupyter Notebook. So it's starting this Jupyter Notebook. And it just takes a moment for it to get started. And so now you can see how this Jupyter Notebook is structured. So these are the gray portions are executable code. And these, and additionally, it essentially breaks it down into sections of what's going on. Some of the other Jupyter Notebooks have additional narrative written around them of what's going on. But for this case, because it's short, I'm going to explain what's going on. So all of our Jupyter Notebooks typically start with imports. You're importing common libraries that are needed to get going, such as the JSON library, the OpenCV library for Python and Matplot, as well as the OpenVINO inference engine for the IE core. Now you're loading the network, you're establishing the core object. Remember in the original common workflow, you're reading in the network, and so reading in the XML and the bin file. You're setting the device, in this case, to CPU, and then you're setting the input and the output of the essentially the blob keys. And I'm going to start running this. So how to run this is you can just hit this, and it'll run. And then you can hit the next one, and it'll run. And if it had a printf, it would display that as well. Now, getting down to here, when you're loading in the image, this one is loading the image of the flat-coded retriever, and this image file is called Coco JPG. It's resizing the image, it's transposing it. So I'm going to run it, and it shows the image. So it shows sort of like the matplotlib, which is sort of the matrix of the image itself. That's why it was important to load that file, because you're loading the image sort of into a matrix of data. Then you're going to do the inference. So it's run the inference in the background with the image key and running it to the exec net and the infer API. And then you are going to convert it. So this converts and is really processing the data, and it outputs and it tells you that it was a flat coded retriever. So that was the output of this very simple hello world Jupyter Notebook. So the Intel DevCloud for the Edge is a great place to also get started. It's an environment that has OpenVINO installed, and you can use it to do instant AI inference. Essentially, it's a lab for your own project. There's no fees to join, so you don't have to account for any budget or shipping or setup or maintenance of any equipment. It's 90 days of access, and you can extend it as well. You can learn with the Jupyter Notebooks that we have online as well there. They execute to compute power that's in the cloud. You can prototype on all sorts of edge hardware. So you get up to 50 gigs of private storage space. You can upload your own data sets and code, or you can code right there in the cloud. And you can also download those files so you won't lose them. But how this works is really, we have a whole bunch of edge hardware. So we have examples of Intel CPUs and GPUs and VPUs, our vision processing units, so our Movidian Myriad X chipset. And There's a core sort of development servers that are Xeon based. The Jupyter notebooks run on the Xeon based development servers. But when you want to essentially you connect through HTTP. There's a website, very easy to connect, and I'll show you the method for connecting and signing up. And then you can execute your application, your inference, to a job queue. And the job queue, you can specify the device that you want to set it to, one of these devices. And you can run the inference, you can run the inference, and then you can see the output of your video or your image output of how it performed. Now, we initially offered this really for a development environment, particularly for software developers, enterprise developers out there who are trying to decide which sort of architecture they want to deploy their inference and want to compare and contrast. But because of the power of the Jupyter notebooks, it's also a tremendously capable way of learning about OpenVINO. And so we have enterprise developers who are learning with the developer cloud. We have sample applications by vertical in the developer cloud. So again, these are sample applications that you can see the code, you can see how they're instrumented to do things for safety or healthcare or retail, industrial, and so forth. So let's do a little demo on the Intel Developer Cloud for the Edge. So a great place to start is if you wanted to go to software.intel.com/IoT. And you'll see here Intel DevCloud for the Edge, and you can get access just by going there. Now, I've already gone there, and I've already signed in just for the sake of streamlining this. But you'll register and sign in for access. And the home page will list you, essentially guide you through a learning phase, a build, and an optimize phase, and then launch in terms of if you want to get down to the point where you actually want to deploy a solution. In the Learn tab, we have sample tutorials and the sample application. So this is where you'll find the more starter tutorials and the sample applications. And here also we give the overview that I kind of showed you as well already, but you can go back here and re-review. And if I go to tutorials, you'll see 8 starter Jupyter Notebook tutorials. You can do things and it'll teach you how to migrate to the DevCloud. Say you have code and data sets you want to migrate up to the DevCloud, or migrate down to your local machine, either your laptop or an edge device. Teaches you how to get that code and those files back down. Here's a tutorial on OpenCV. Great starter tutorial for people new to OpenCV. We have things on using encryption with object detection. We have a benchmark app, and then 3 sort of great starter tutorials for AI computer vision or style transfer, which is sort of an artsy way of converting maybe an image where you have an image and you take another image, like maybe a very well-known image like Starry Night, Van Gogh's Starry Night, and you want to apply the stylistic aspects of that image to your own image. 2 other starter tutorials, object detection and classification, to really detect objects and then to classify objects. And I'm going to start the object detection Jupyter Notebook, and it'll look very similar to the previous Jupyter Notebook in sort of how it looks in sort of executable code surrounded by narrative. But this is running in the cloud, in the DevCloud for the Edge. So in this Jupyter Notebook, it's a bit more explanatory, has more narrative. So there's prerequisites. It talks about the Jupyter Notebook itself and all the files that are available to you. So face, car, images that are used in this documentation, the model itself, the XML file, and so forth. It gives you a bit of an introduction on OpenVINO and on the model, and you can link to find out more about this AI pre-trained model, the MobileNet SSD. Key concepts, which we've already gone through about using a trained model, model optimizer, the inference engine to deploy in a user application. So scrolling down, we get to essentially that common workflow about establishing the core object, loading the plugin, reading the IR files in, setting the plugin, preparing your input, running the inference, and processing the output. Now, this section is talking about reformatting the image using OpenCV. Now, it talks a bit about the imports of common modules, Python modules that you need to import to run. And this is the executable code. So if I run here, it says imported Python module successfully. Now, if you want to run creating the IR files for the inference model, this section is downloading the model, and then it's converting the model using the model optimizer with the command of converter.py. And you can see it specifies the model, the MobileNet SSD, and the output. So now in the configuration section, you're going to run this portion of the code, and you're essentially setting a parameter of the model XML and bin to these files for that model. You're setting what the input path is of the image that you're going to do inference on, and then the path for the CPU extension library, and the device that you're going to set, in this case, CPU. The labels path, many models are trained and have a set of types of objects that they're trained to detect. And in the labels.txt file, in this case, this model, I think, is about 1,000 different objects that it's been trained to detect and to tell you what they are. It'll do some printfs as well. So we'll run it. And so it did the printfs. Then you create the core inference engine object. So inference object has been created. Then you essentially load the network. So you're loading the bin and XML files. It's checking for some errors, and it's fine. You're loading the model and the blobs, and you're reading in the model. You're preparing your inputs. You're doing the actual resizing on your image to make sure the input is how the model defines how it needs to be input. So you can see in this car, and here's the image that's been used. And here's the sort of the matrix, the matplotlib of that image. So now we're getting to the point where we need to run the inference. So you're going to inference, and you're going to, it's actually going to, you're going to time how long it takes. So the inference ran, and it took a little over 57 milliseconds to run. And then you're going to process the results. So all of this code essentially defines how and gives you sort of describes for you and code that you can reapply to essentially process your results. So the results have been processed. Now we're going to break it down into this display the results. And in this case, the model is defined to identify the car and to do a bounding box around the car. And it told you a percentage of how correct it is, 100% correct that it's a car. Now in this particular tutorial, you can do additional things, and I won't do it for the sake of time, but you can run different models, and you can run your own image. So you can set the path to run your own image, and you can run on video as well. So a lot of things that you can learn just from this Jupyter notebook alone. So some resources that are available and community support. So great place to start. I mentioned, use a pre-trained model. Check our Open Model Zoo for a public or an Intel pre-trained model. Download the OpenVINO Toolkit. A great place to start. I'm going to sort of show you, if we go back to the Intel Developer Zone. Here's the OpenVINO Toolkit if you want to get started. So you can download the toolkit, and you can select from Windows, Linux. Mac OS works, but it's a very specific release, and it has to be an Intel-based Mac. The newer Macs aren't supported with OpenVINO. So I recommend starting with Windows or Linux if you prefer, and you can download this to your system. There are also instructions on sort of the prerequisites that you'll need to install, such as CMake, Python, in the case of Windows, Visual Studio C++. So in the prepare phase, you're really gonna, you might wanna start with some demos or use some of the tools and the model optimizer, for example. You may wanna learn how and get some practice with, say, converting an FP32 to an FP16 to remind you that you need to use an FP16 and model formatted in this hackathon with the device that we're supplying. But there's other capabilities here you could learn more about. Our deep learning workbench, which is a GUI-based tool to really sort of compare the accuracy and see how visually the metrics of the model, reference implementations, sort of best performance practices, and then deployment manager if you want to get beyond the sort of, that's probably a bit beyond the stage of hackathon. But then also, if you're looking for support, we have community support. So there's a way to essentially submit a question about OpenVINO. We also, for the purpose of the hackathon, have a Slack channel as well to answer specifically questions for this audience, for you. Also, another great way to learn, we have an Edge AI certification. It's a great way to upskill. It harnesses the power of the Intel DevCloud for the Edge and sort of video training content that trains you through OpenVINO itself in more in depth and trains you using the 3 starter tutorials and the Jupyter Notebook. So it gives you hands-on experience. And it also rewards you some prizes that you can get redeemable through chips. And it's a great way to upskill on your resume and put something on your resume. All the content is free to go through. There's only a charge for the badge of $99, but you can go through all the learning content and decide at the end if you want to have the badge for your resume. By all means, available, but certainly not required for the hackathon. For ideas, we have a blog site at Intel. It's called Intel DevMesh, and you can explore projects from the community. So these are projects that have been developed by people outside of Intel, some inside, but many, many, many from outside of Intel, who are doing things using Intel technologies. And some of them use OpenVINO to do inference and, for example, detecting for PPE or detecting for, say, plant health or in healthcare use cases. We also, for students who are dialing in and part of a hackathon, if you are very, you want to be an evangelist for Intel, you can participate in the Intel Student Ambassador Program, and you can get sort of access to software and tools. You can also get early access to information and hardware under NDA. And we really look for these students because we look for them to be advocates for us on school campuses. Visit the Intel Developer Zone. I mentioned I kind of already showed you going to software.intel.com/IoT. Explore our reference implementations. You can download free software. We have developer kits there you could explore, but we are going to supply the Luxonis devices to the selected teams for the hackathon. You can learn more about other things that are critical to IoT. You can collaborate with our ecosystem, and you can find our support forums. So are you ready to get started? So I have some homework for you. So number 1, try out the Intel DevCloud for the Edge. Go to devcloud.intel.com/edge or just Google Intel OpenVINO DevCloud and you'll find it. We actually have a number of DevClouds at Intel. We're the Edge focused one. Start learning there on your journey to being prepared for hacking at the hackathon during the 48 hours of the hackathon. Also, download OpenVINO to your own Intel-based laptop. You can do and will be able to do a tremendous amount on your own laptop, particularly as you enter in the hackathon time period. But you can also start learning now in advance of the hackathon. Try out our Jupyter notebooks, start learning from those. I already mentioned, I think that's the best place to get started, in conjunction with downloading and installing OpenVINO, and then using the Jupyter notebooks we have on GitHub to install on your own laptop to run those and learn from those experiences. So there's a lot of companies that are deploying OpenVINO. And the only reason I bring this slide up is that in the context, I speak to faculty and students all the time, is that there's a growing industry that needs talent. There's companies that need talent that understand AI, need to understand OpenVINO. So if you're at your point in your career and you're starting with AI, and maybe at school, or you're in your point in your career a little further on and you're really trying to upskill, you're at a great time, and you're at the inflection point of AI, because there are going to be jobs for years to come in the space of AI. So really, we really want to reimagine how people and data can change our world for the better. I mean, that's what's driving Intel, is to improve the world for everyone, all of us.